Good evening, everyone, and welcome to this Institute lecture to be delivered by Professor Vikram Jairam from Indian Institute of Science, Bangalore. I'm sure you are already familiar with the topic. That's why I think you have been drawn to this lecture today. So it is on the brief history of irreversible thermodynamics and thermoelectricity. So I am Ashutosh Gandhi, a professor in metallurgical engineering and material science here in IIT Bombay, and it is my pleasure to welcome Professor Vikram Jairam to this institute lecture. I thank you for accepting our invitation to deliver this lecture today, and I would like to briefly introduce Professor Vikram Jairam. He is an honorary professor at the Department of Materials Engineering at the Indian Institute of Science. Prior to taking up the position of honorary professor, he had a long career as a regular faculty member at IISc. He served as the department chair, then he was the dean of mechanical sciences there. Vikram has also been on many committees which review or sponsor research in India, and he has been active in many professional organizations. But to me, the most important aspect of him is the broad spectrum of research topics that he has worked in, which will be quite apparent just looking at the title of the talk and the kind of work that he has published. It's a very wide range of topics, starting from electron microscopy, then composite materials, and then metastable materials, mechanical behavior of materials at small length scales, high temperature materials, and so on. So he has published his research in close to 200 papers. He has guided more than 25 PhD students. So I am sure that you are all looking forward to hearing Professor Vikram Jairam. So without taking any more time, I request Vikram to please deliver his lecture.
So, thank you, Professor Gandhi. It's a pleasure and an honor to be here. He made only one error in his introduction. I don't actually do any research in this area. I'm a bit of a novice. So, an occasion like this one has to choose a topic which is sufficiently earth-shaking for the future, or perhaps was earth-shaking once upon a time. It's dangerous to predict the future. Besides, the only thing people are interested in these days is machine learning and climate change. And I don't know, I know even less about that than thermoelectrics. So I decided to go back into the past. I think that I escaped the kind of lives that some of the younger people here are facing. Namely, you don't have time for anything. You're always doing something. And so I thought it would be nice to provide a perspective on how some of the important ideas which affect a wide branch of systems in physics and materials and chemistry evolved. Now, that also sounds a little pious. The real reason is that I started teaching a course a few years ago. And when you start teaching a new course, you ask a lot of simple questions. Most of those simple questions are also stupid questions. And if you ask the right people or read the right book, you'll find the answer pretty quickly. But some of them, the answers are not so clear. So in the course I was teaching, I had one module which deserved one lecture on the subject of thermoelectrics. Now, thermoelectrics are a strange mix of something which is fascinating and largely useless. I hope I'm not annoying or insulting anybody here. People still think of thermoelectrics as basically thermocouples and Peltier cooling. And largely that is what it is. All the energy conversion and so on that is being talked about is yet to really make an impact. On the other hand, the physics is extremely rich, and it has three sources. The first is a sort of a continuum approach, a thermodynamic approach to what thermoelectrics is all about. And that's really what I want to focus on. And that's not dealt with much when people teach today. The obsession today is with either DFT and finding new materials. And this is where the richness comes in. The physics part of thermoelectrics is the finding of materials with very contradictory properties. You need high electrical conductivity, but then you also need a high Seebeck coefficient, which means you need something where the carrier concentration changes with temperature. You also need very good thermal insulation. So there's a contradiction right there. So the band structure of materials that satisfy all these properties is something which is rather restricted. And the third aspect is microstructure, and this is where all the metallurgists dive in. Because in order to achieve this combination of properties, one needs to, well, one of the things one needs to do is create interfaces, refine the microstructure, multi-layers, voids, porosity, and other kinds of things. In the midst of all this, the basic ideas which govern this phenomenon, which is basically a coupling between two transport processes. You have heat flow on the one hand, and you have current on the other. It was never, the books I read never convinced me what was going on. So I had to undertake a little personal journey, and this is the story of that journey. So I hope you'll find it amusing. The story is really something about heat, and it's about two individuals. And these are the two individuals. This is Lord Kelvin and William Thomson and Onsager. Kelvin, of course, everybody knows. Onsager, the people who are really into thermodynamics here will know about. But no story of heat is complete without this gentleman, which is Benjamin Thomson. So let me get started. I'll put this in perspective. The end of the 17th century and the early part of the 18th century was when the Industrial Revolution began. Steam. And so one of the earliest vehicles or one of the earliest propulsion systems that was built, or at least one of the earliest records, is this boat. So you will see what happened to Papin's boat. This is still what happens today when a new technology threatens existing jobs. And this is the sort of thing that launched the Industrial Revolution, which marched along. Steam engines were built, and we're still living, and we will continue to live probably the next 100 or 200 years with the thermal conversion of heat into electricity, and engines which propel us, whatever you say about solar power. So at this time, heat was a quantity which was not very well understood. It was thought of as a fluid. The relationship with mechanical energy and so on was obviously not made. That's what the laws of thermodynamics, which came 100 years later, put into perspective. But one of the early characters who I think did a lot of the work which made heat a little familiar to people and which laid the foundation for what people like Clausius, Kelvin, and others did later, was this Benjamin Thomson in the late 1700s. So some of you will know about him as the person who, when he was boring holes in cannons by drilling, measured he didn't do actual measurements, but he determined the amount of heat coming out in relation to the amount of work put in. I mean, that's one of the early examples of the fact that the heat generated was somehow related to the amount of mechanical work done. He also weighed the amount of material that came out of the hole in the cannon and established that there was no difference. In other words, the heat was not a fluid with mass. I mean, all this seems very obvious to you today, but 200, 300 years ago, it wasn't so obvious. So he was a practicing engineer, basically, but he was many other things. Like many people who are smart at one thing, he was smart at other things. He secured his financial future very early, and he married a lady who at that time was old enough to be his mother, probably. And it was important to secure his financial future because you need money to do experiments in heat. There were no research grants at that time. And then he got into politics. His political leanings were such that nobody was quite sure whose side he was on. So that sort of thing will be very familiar to people who know the politicians of today. So he tried to fight with the Americans against the British. He was suspected of being a traitor. He just escaped by the skin of his teeth, and then went to England as advisor to King George. King George, as you will remember, was not a very competent king. He managed to lose the American colonies. So Benjamin Thomson went off to Bavaria, where astonishingly he became a count. And that is where Count Rumford came from. And he became prime minister there. When he became prime minister, one of the things he did was the removal of beggars. Now, begging was a major nuisance. And the way he went about it, there's a relevance to why I'm bringing it here. The way he went about it was a carrot and stick policy. So you can read this part, but basically what he did was to get them off the streets, he threatened them with arrest. But the carrot was, you come to a place where we will give you soup and you can stay. Now, having got them to that place, he needed to get them out. He didn't want to give them soup for the rest of their lives. So the carrot was employment, and the stick was the soup was not very tasty and it didn't come often enough. So this is how he got rid of the people from the streets. But the relevance here is that he had to deal with cooking, which meant managing heat, because a major source of expense when it came to feeding all these people was the fuel cost. So he had to learn how to, well, he used his extensive knowledge of heat he invented the modern kitchen range, the double boiler, the baking oven, the pressure cooker, drip coffee maker, and so on. So enterprising chap, but there are no laws named after him. There are no equations named after him. So after this, the academic work continued in thermodynamics, and you know, all of you learn about that in school and college. The next major thing that happened was in the early 1800s, Seebeck discovered that when you made a junction between two metals and put one end at one temperature and the other end at another temperature, that you developed a voltage. Initially, he thought it was magnetism, and he was corrected by Ørsted, because by then people knew that currents produce magnetic fields and so on. And based on this, he developed what is very similar to the electrochemical series, namely the thermoelectric series. So by that, you can take A and B and C, measure the voltages, and deduce what the voltage and the sign would be for any combination. A little bit later, a French watchmaker, who later gave up making watches to do research in physics, by the name of Peltier, discovered that if you simply passed a current, then you rejected heat at one place and absorbed heat at the other. So if you think about the way this works, remember the second law, you always lose. So the temperature which is higher is the one where heat will be absorbed from. So any temperature gradients will be eliminated. Otherwise, you know, one side will go on getting hotter and the other side will go on getting colder. So this is what is now used as Peltier cooling. And in fact, another person by the name of Lenz used this effect to actually freeze small quantities of water by passing current. And this is where things stood until William Thomson, that is Kelvin, came onto the scene. So Kelvin, he was a bit of there's a public perception of him as a villain. I'm not quite sure where this comes from. But if some of you have seen the film Around the World in 80 Days, not the most recent one, but one a little before, the villain there is Kelvin. And there he's the president of the Royal Society. And unlike the book, where Kelvin has no role to play, in the movie, having taken the bet with Phineas Fogg that you can't go around the world in 80 days, he then sets a bunch of hoodlums and criminals after him to make sure that he fails. And there is also a villain called Kelvin in a Japanese comic series. Now, I assume it's the same one because Kelvin is not a very common Japanese name. So again, for some reason, he appears to have sort of inspired people to think of him as a bit of a malicious character. But anyway, he was no stranger to controversy. And one of the earliest controversies that he had to deal with was the age of the Earth. So when he was 17, the solution for heat conduction by Fourier had just come out. This is the solution to the heat conduction equation, the series solution. And using that, he estimated the age of the Earth by making certain assumptions, namely that there was a solid ball of some temperature, of high temperature, everything was molten, and it is then cooling by radiation. So you can estimate how much heat is lost from the surface, and then you assume that heat is conducted from the interior to the outside by a mechanism which involved the thermal conductivity, and you had to make some estimates of what the thermal conductivity was. So this red band here, now you can't read this, but what is shown here is the depth into the Earth, and this is the temperature. So this is a little different from normally you would see temperature on the y-axis and distance on the x-axis. This is reversed. The point is simple. If the Earth is young, the temperature gradient here would be steep. If the Earth is old, heat would have had time to diffuse from the interior to the surface. And so the temperature gradient would not be that large. So the estimates of the temperature gradient at the surface were just beginning to come out. And so the range that he got here, the mean is around 100 million years. The scatter is quite substantial, it's between about 10 and 200 or 300 million years. Now this caused a lot of problems. And the problems came from several sources, because just a few years later came the publication of The Origin of Species by Darwin. And this required an age of the Earth, after it became cold enough to inhabit life, of hundreds of millions of years. And this number was simply not compatible with the heat transfer, that Kelvin got. The church, of course, had its own ways of calculating the age of the Earth. But even if you dismiss those, there was another problem. geologists at that time, they thought the Earth had lived forever. And there are no geologists in the audience, because there's an interesting conversation between Kelvin and a Scottish geologist about the age of the Earth. So you will see that this conversation is not very informative. It basically ends by saying, well, you don't know what you're talking about, and the other person saying, well, if you had any brains, you'd know what I'm talking about. So that's the situation in which the controversy began. Now, in the popular understanding, the way this was resolved is through radioactivity. And this was popularized by Lord Rutherford himself, who was never reluctant to popularize himself. And he describes what happened when he was speaking on radium at the Royal Society, that he knew he was going to say something which Kelvin wouldn't like. Fortunately, Kelvin fell asleep like many professors do, but then he woke up at the right time. And then Rutherford was inspired to say, well, he was perfectly correct, but he didn't know about radioactivity and the source of heat that represented, and therefore you can't blame him for being wrong. Now, this is unfortunately not the whole story. Radioactivity doesn't produce enough heat, number one. And secondly, it doesn't change the gradient because it simply generates more heat everywhere. So the key issue was not the temperature, it was more the gradient of the temperature. And it turns out that the problem was one of some other mechanism of transporting heat from the inside to the outside, not just assuming it was thermal conduction. And this came up from John Perry, who was Kelvin's assistant. Today you would call him a research associate or a postdoc. He got the same respect for arguing with Kelvin that a research associate would get for arguing with a supervisor. Namely, he was ignored. But what he said was, yeah, we know that there's thermal conductivity, but the stuff is very hot, and over hundreds of thousands of years, there may be another way of moving material from the inside to the outside. If you're moving material, then of course there's another way of transporting heat. Of course, he's perfectly correct. This is something, by the way, that Heaviside had also proposed. Heaviside, some of you will know from his, he was the one who converted Maxwell's equations into the form. He was responsible for a lot of long distance communication, the inventions associated with that in the Heaviside layer, which reflects. And basically this goes back to the fact of how you cook birds. You cook them up to a certain point, and then you let the heat from inside slowly diffuse outside. If you try to cook everything, then you'll overcook one part in relation to another. So you'll see that if you have a particular thermal gradient, if you only assume conduction, you may get an age here, which is about 100 million years. But if you assume transport of material, then you can get an age which is closer to what the age of the Earth is. And this transport of material is, of course, what we know now as core mantle convection. So this was all not known then, that the Earth was on a there was a crust floating on a very viscous underlying substrate, and so on. So many of the ideas, nobody looked at a map of Africa and South America and say, oh, these things are joined together at some point. So this was that controversy. Now let's come to thermoelectrics. So this was his first very early statements, which came probably a few years after the statement of the second law, which everybody is familiar with. So the second law, remember, dealt with equilibrium systems at equilibrium. All these state functions and things, free energy, entropy, and so on, are defined for a system for which nothing is happening. But he now said that the flow of current in a conductor can be converted into heat in two ways. The one is the normal thing that we think of as Joule heating, which is proportional to the square of the current, and that had been postulated a few years before. But the other was a reversible conversion of heat into work that followed the same laws as a Carnot cycle. It's a very bold statement, but that's what he did. And he assumed that this was proportional to current in the first order. That is, the heat is proportional to the current, like the Peltier heat, for example. In other words, when heat flowed from a hotter region to a colder region, it can do work. And that one could apply what we now call the second law of thermodynamics to the process. Now, this is not a classical reversible change, because remember, in a reversible change, you always talk of a process which can be taken in the limit to the point where nothing happens. But here, you can't go to the limit, because if there's no current, then there's no there's no thermoelectricity. So there's always a finite conduction of heat or a finite potential difference. There's either heat flow or there's current flow. So this is not a system in equilibrium. So this is the thought experiment he did. Supposing you had a series of materials are n equals to 1, 2, 3, 4 up to n, and these are junctions at different temperatures. Well, the temperature basically changes from T0 to T1 in one, T1 to T2 in 2, and so on. And you can imagine, so I'm just using the original terminology that he used. F was the voltage developed, gamma is the current, B is what you would call the resistance, because that is the term which corresponds to heat dissipation, and A gamma is the work done. It's the electrical work done. So you're simply balancing these two terms. So imagine you put a dynamo here and you balance the voltage that this thermal circuit produced against the dynamo. You could apply a voltage which ensured that there was no current, or you could short circuit the two and have a current flowing. So if you do this, you see, you can make gamma sufficiently small that gamma squared becomes small compared to gamma. So in theory, you can eliminate the resistive dissipation of heat in relation to the mechanical conversion or the electrical conversion of heat into electricity, and therefore you can make this as small as you want, in which case the thermoelectric voltage is only related to this quantity A, and A now depends on this circuit. So the question is, what is that circuit? It has a number of temperatures here. So A here is nothing more than the sum of these coefficients alpha, which relate the voltage to the temperature at each point. So this is the first law, it's just conservation of energy. The second law simply tells you that alpha gamma, that is the voltage times the current divided by T, the sum of that has to be 0. That's what we would call the entropy. So except this was 10 years before the term entropy was coined, and therefore this basically represents the statement of the second law for a reversible change. And so what are these various terms alpha? So you have two things. You have the conversion of current to heat at a junction. So you have two materials and a junction at one temperature, and then you also have the current to heat and a temperature gradient in a single material. So that sounds a bit confusing. Remember that this is the junction here between 1 and 2 at some temperature T1, but then in material 2 the temperature varies from T1 to T2. So you have two effects, and the second one is what's called the Thomson effect, because he had to invent that in order to make sense. So he said that there is a conversion of current to heat in a temperature gradient, and the combination of the two is what you observe as a Seebeck effect. So if you now write down the first law, the voltage you develop is due to these combinations of what you would now call Peltier heat, plus the heat the voltage developed in individual materials across a temperature gradient. So you have junctions at a fixed temperature between two different materials, and you have a gradient of temperature in a single material, and you're simply summing all of them. This is the first law, and the next one is the second law, which takes the same terms pi 1 and divides by T1, and again sums all this, and this has to be equal to 0. Now this is a general equation. If you simply reduce this to two elements, so you have to have two, otherwise there's no junction here, then you will get these famous Kelvin relationships, which tells you that first of all that there's a relationship between the Peltier coefficient and the Seebeck coefficient and the others, and so these have stood the test of time. And to appreciate what was done here, so this is the rate of change of the Peltier coefficient with temperature. This is the sum of the Seebeck coefficient and the Thomson coefficient, and so on. So I just want to put this in perspective. This is perfectly general. All these coefficients can change with temperature. Thermoelectric heat is assumed to flow along the wire. You don't lose it on the sides. Joule heating, remember, is rendered negligible by making the current sufficiently small that I squared R is small compared to the thermoelectric part. Kelvin did not know what electricity was. Nobody else knew either, because the electron hadn't been discovered then. It was another 20 years before the electron was discovered by a nephew of his, another Thomson. He didn't care about mechanisms, energy bands and Fermi levels and so on, where it's probably 50 years in the future, 75 years in the future. This is an excellent example of how with thermodynamics you can say very profound things while knowing nothing about what's going on. So conduction of heat from high to low temperature was ignored. So in a measurement, you can't avoid it. Fourier's law is there, happening whether you like it or not. And the Thomson coefficient is a sort of a specific heat, not of charge, but of flowing charge. That is, flowing charge is associated with an absorption of heat. A few years later, this same idea was extended to solutions, electrolytes in potential gradients. This is by Helmholtz. He used very similar arguments, and that's what led to the double layer and many things that we now know what happens when an interface is created between a solid and an electrolyte. Thermodiffusion, and then the behavior of electrolytes in temperature gradients. So I'll sort of knit all this up a bit later. So the point is there are different combinations of effects which are all coupled. So if you were to summarize, you can think of the current density as due to Ohm's law, and this is Ohm's law. It's basically the conductivity times the electric field, and Seebeck. which is alpha times the temperature gradient, and heat flow. And heat flow has a traditional Fourier's equation here, which is thermal conductivity times the temperature gradient, plus this Peltier combination. And the interesting part was, in both cases, this same coefficient came up. And the question was, why? So Kelvin understood the limitations of what he was doing. I mean, he says that repeatedly, that he's applying concepts in reversible thermodynamics to an inherently non-irreversible process. And there are some and this simply highlights the problem. The conversion of current to heat is reversible, and so is the current of heat flow into current. But the conduction of heat is treated as an irreversible effect. The same thing happens in an electrochemical cell with concentration gradients. The diffusion of electrolytes is irreversible, but ion transport is reversible. But in thermophoresis, which is diffusion in a temperature gradient, diffusion due to thermal gradients is reversible. So, not very clear what process is reversible when and is treated as irreversible in some other situations. And eventually, we will look at situations where only one process exists. And material scientists are very familiar with that. When you have diffusion in a crystal, you have only diffusion. But you know that you can have diffusion along x1 due to a concentration gradient along x2, and you have diffusion along x2 due to a concentration gradient along x1. Both processes are diffusion. So you can't say one is reversible and the other is irreversible. So this issue was something that clearly was not based on very strong fundamental foundations. So before getting into that, I just want to do cover some elementary issues regarding driving forces and responses. So this is some very simple physical chemistry here. So we all know this Clapeyron equation, the change in free energy. So let's take water, the equilibrium between water and ice. So if we have water and ice together and they remain in equilibrium, a little bit of ice melts, the net free energy change is this. It's just plugging in the entropies of the various phases and the volumes of the various phases. And this has to be equal to 0. And this is what defines the pressure temperature equilibrium line, which means P and T, changes in P and T need to follow a specific function. By the way, this is can be used as a principle for refrigeration. So here's an example of a shape memory alloy, which is used. There's a startup company in California. I wrote to them asking them for details. They never replied. But it's there on a website somewhere, that they're using the martensitic transformation between the austenite and the martensite, which either one direction it evolves heat, in the other direction it absorbs heat, to run a refrigerator. So there'll be no moving parts here and no noxious gases. Now you know that if you differentiate this free energy twice with respect to temperature keeping pressure constant and then reversing the order, you can prove obscure relationships like this. This quantity here is a volumetric expansion. Thermal expansion coefficient, and that is equal to the rate of change of entropy with pressure. And nobody knows what the hell this means. Everybody thinks they understand what the volumetric expansion is. So you can prove such obscure things and torture students with it. But remember, you can do all this because they are state functions, and it doesn't matter what order you do the differentiation. The state, the free energy or the entropy of a system is defined entirely by the pressure and temperature. Now this is for a scalar system. You can do this for the different directions, properties along different directions for a vector state function. So let's take electrostatics, where let's say the internal energy due to the electrostatic field E, which produces a displacement or charge density D, dd, is given by this term. But dd itself depends on the dielectric constant along different directions. So if you take the partial derivative of W with respect to E1 and E2 and then E2 and E1 in different order, you can show that epsilon 1 2 is equal to epsilon 2 1. And so this is no end of the kind of relationships you can prove. This is in piezoelectricity, the strain with respect to field is equal to the displacement with respect to stress, keeping certain things constant. But this is for thermodynamic state functions. So irreversible processes are transport processes. Things are not in equilibrium. So now let's look at non-equilibrium systems. Again, I want to dismiss some simple ideas. I had to go through it myself. So I tried it out on my children to see if they understood it, and then on some undergraduates with varying degrees of success. So the first question is, why does a bucket of water cool to below ambient temperature? So I tried this with my undergraduates. I got a variety of bewildering answers of why, if you just leave water out, the temperature can actually fall below the outside temperature. Now here what is happening is that the gradients in water vapor activity are driving evaporation. And so when the vapor disappears, it is taking latent heat with it and the water temperature drops. But it's the gradients in temperature which drive heat conduction. And so if you make the thermal conductivity sufficient, or you don't allow convection or anything to happen, you thermally isolate the system, the heat will not flow back. So you can locally cool the water. Now each one drives its own process. Water vapor activity gradients drive evaporation. Temperature gradients drive heat conduction. The question is whether gradients in something can drive something else altogether. And this is something that happens all the time. And that's really what thermoelectricity is all about. It's a gradient in temperature which is driving current. It's like you have a temperature gradient in a pipe and suddenly a current starts flowing along it. And this was an example of this that was known about. It's been known for a few hundred years. But the one that was tried during the separation of U-238 and 235 is the knowledge that it's basically thermophoresis. That is, if you have a mixture of gases in a temperature gradient, they will separate. So they tried to separate U-238 and 235. It didn't really work, but it's an example of the kind of process we're looking at. And so this brings us to Onsager. The interesting character, the whole interesting character. His first job was teaching chemistry at Johns Hopkins. And he was sacked after 1 year. He was sacked because the students, he was a first year chemistry student, they didn't understand what he was talking about. This is not surprising because his faculty colleagues didn't understand what he was talking about, and he used the same tone with them. You must remember in those days, student fees in private universities was what drove everything. There were no large research grants. So he was sacked, and then he went to Brown. And this is where he wrote the famous papers. He did many things, but the one I'm going to talk about are the reciprocity relations at Brown. But there, after a few years, he was allowed to leave, as the euphemism goes, because probably the time of the Depression, they couldn't afford him. And he settled in Yale, where he retired and died. And he occupied the chair that was named after Gibbs at that time. I think Yale was probably used to obscure thermodynamicists by then. So at one point, the president of Yale decided that all his faculty should have doctorates. So Onsager's head of department, chemistry department, called him up and said, Onsager, why don't you write something up? We'll get you a PhD. And so he wrote up a thesis on Matthew's equation. I don't know of any mathematicians here, but Matthew's equations is a solution to the vibrations of an elliptical drum. And of course, his head of department had no idea what the thesis was about. So the mathematics head slyly suggested that they'd be happy to sponsor the thesis for a PhD in their department, but this was an insult. So the chemistry head took off Onsager's name from the thesis and sent it to leading experts around the world and said, tell me, is this worthy? Now, every academic dean knows what happens when you do this. Either people don't respond, or they say they'll respond and they don't respond. So after months and much pestering, came back a reply from one of the experts in Europe who said, thank you for sending me this thesis. I apologize for the delay. It's all very profound and extremely erudite and well written. And I can't pretend to understand very much of it. But what I really don't understand is why you sent it to me. You should have sent it to Onsager. So, so this is what he did. And this is really, as far as I can tell, the onset of the whole formalism of how to deal with irreversible situations in thermodynamics. Supposing you have a reservoir at T and a reservoir at T minus delta T. And there's a heat flux. So this slab here has a temperature gradient or a temperature profile which is independent of time. This is an infinite reservoir, this is an infinite reservoir, so the temperature remains here constant. The amount of entropy lost here is Q divided by T, and the entropy gained here is Q divided by T minus delta T. So there is a difference. And where is that difference coming from? Because this system doesn't change with time, but the entropy is going on changing. So it must be generated in the slab. So this is the notion that a non-equilibrium situation here, which involves exchange of, in this case, heat, involves entropy production. So if you write it, the rate of production of entropy is simply JQ by T minus delta T minus JQ by T. And so the rate of entropy production is this flux times what is now called a driving force, namely the gradient of 1 by temperature. So this is how the whole idea of entropy production was related to a driving force and a flux. And it was assumed, and this is the small deviation from equilibrium approximation that he used, that the flux was also proportional to the driving force. So if you have multiple driving forces, let's say you have matter transport as well as heat, so you can do thought experiments like this, a reservoir and a cylinder, you can have a rate of entropy production which involves a flux of, either internal energy or heat, I've put it in both terms, as well as a flux of mass, which will be related to the activity or the chemical potential. So we can now write the flux of heat as due to not only the temperature gradient, but also due to a gradient that involves other quantities. So these are the two driving forces here, a chemical potential gradient and a temperature gradient. So you now have a mass transport term which depends on both gradients or both driving forces, and a heat transfer gradient which depends on both driving forces. And really what Onsager set out to show was, because he was inspired by the Kelvin relationships, and that's where the thermoelectricity comes in. This is the first example of where you had this cross term of the Seebeck effect and the Peltier coefficient both being equal, both being described by this quantity alpha. And so his objective was to prove that the B is equal to C here. By the way, it had been proved long ago, and not proved, measured long ago. And there's some very clever experiments on heat conduction, which looked at heating things in such a way and then measuring the profile of the constant temperature isotherms on a plate, and showing that in order for the isotherm to be the way it is, the cross terms, that is, if I can just jump ahead, the thermal conductivity K12, which is the conductivity along x1 due to a gradient along x2, is the same as the reverse term. If it weren't true, then the experiment wouldn't. So people knew that these cross terms were equal. And remember, these are equal for non-state functions. So this is not like the dielectric constant or the elastic modulus or something. So this is the outline of the proof. So he said thermodynamic equilibrium is not a static thing, it's a dynamic process. And molecules exchange energy amongst themselves, configurations keep changing, but the overall distribution remains the same. Okay, we all agree on that. The reversibility, and this is really one of the heart of the argument, of molecular velocity suggests that if a configuration changes from A to B, the probability of going A to B is the same as going B to A. So this is what's called microscopic reversibility. Even in equilibrium, fluctuations occur. So the probability that there's a particular distribution of energies, is very strongly peaked about what is eventually seen as the Boltzmann distribution. But there is a probability of a fluctuation about that. And when it happens, and I think this is really the key. If you understand this, then you can follow everything else. The way the microscopic fluctuations return to zero is the same as if you impose an external temperature gradient. In other words, when you impose an external temperature gradient, it looks like you're driving heat from one place to another. But if you have a microscopic fluctuation, in effect, there is a momentary period in time when the energy is not uniform, but it very rapidly exchanges energy in order to come back. So what he said was that process is the same. So you can apply to macroscopic, externally imposed heat fluxes the same thing that is happening in a microscopic system which is fluctuating about its mean position. And so what he calculates is the energy density of the fluctuation about its centroid. Its magnitude represents the strength of the fluctuation. Perfect equilibrium, it would be zero, of course. And now by doing it this way, he made the proof sufficiently general that it could be applied to anything. And we'll see the variety of phenomena that it can be applied to later. So if you read his 1931 paper, this is the one that set it out, these ideas developed from equilibrium in a chemical system. So supposing you have a molecule that exists in three different forms. Took the case of a sugar, I don't know about the galactose, never heard of it before I read this paper. So it exists in three different forms. So you can imagine an equilibrium that exists. So the rate of change of, let's say, form A will depend on a rate constant, which is the rate at which A becomes B or A becomes C times the number of A, and the reverse process, that is the number of B which convert to A according to the number of B's which are present and a rate constant. So you can write these three equations down, and supposing the system is at equilibrium with certain values n star. So n, A and B, A, B, C are arbitrary variables, but n star is the equilibrium values. Since the system is at equilibrium, the rate of change of n star of any of these with respect to time will be zero, and it stipulates three conditions subject to the constraint of conservation of material. But now there's an additional constraint that people instinctively impose, and that is that these two are equal. That is, KAB and B star is the same as KBA and A star, and that leads to another condition. And the reason he gives is that if you did not have this condition, then you would have to maintain equilibrium by processes where A went to B, B went to C, and C went to A. And that cyclic process was somehow miraculously maintained equilibrium. Now, this is something that he said chemists don't like. They believe that equilibrium is maintained by the forward and backward processes simultaneously, not through some complicated circuit which comes back to the same thing. So this was his starting point. So from here he looked at a chemical reaction away from equilibrium, and so again you write the flux in terms of a driving force. The driving forces are called x, and the L's are what are now the famous Onsager coefficients. And if you linearize this expression, so this is written in linear form, then you can show that the same chemical reaction that we wrote earlier, which tells you the rate of change, XA now is the deviation from equilibrium. So it's Na minus Na star. Na is the actual quantity and Na star is the equilibrium value, can be written in terms of a driving force. This is just simple chemical potentials. So a driving force XA, which is simply the chemical potential of this of A, times one of these coefficients, which tells you how fast it happens. Nothing new, just writing the same thing. This is just to satisfy himself that this made sense. He then applied, and the idea was that these two terms have to be equal, the diagonal coefficients. So he took the problem of heat conduction in a crystal with six-fold symmetry. Now in a crystal, you know that symmetry considerations can make certain quantities zero or equal. So if you have six-fold symmetry, then, so these are the heat conduction laws. So the reason it's written like this is that the driving forces in this terminology are not dt by dx, but 1 by t dt by dx. So we'll see the reason for that later, or what the consequences are. If you don't do that, these two coefficients won't be the same. And the reason you're doing that is that the driving force for, remember, for entropy production, which is treated as a flux times a driving force, is actually 1 by t times dt by dx. So six-fold symmetry means along the x3 axis that L13, 31, 23 and 32 will be 0. But if you say clockwise rotations are not the same as anti-clockwise rotations, then L12 is minus L21. And the task is to show that L12 and L21 are equal. Because they are equal and each is equal to the negative, then it becomes 0. And this was shown by Voigt, whom you'll remember from the modulus averages in the 19th century. But basically he looked at the energy density of the crystal, which is basically the energy per unit volume integrated over the volume multiplied by the distance from the centroid. So this quantity alpha 1 here is going to be 0 if the energy is at the origin, but if there is a fluctuation which moves that away from the center, then it will have a finite value. Over a period of time, of course, it will return to 0. But this alpha 1 represents, if you like, an instantaneous deviation in the energy density from 0 along the x1 direction, and likewise alpha 2 along x2. The mean of each of these is going to be 0, because on average there are no changes. The product, the average of the products will also be 0, and the means, the mean squared averages are going to be equal along these two directions. So every fluctuation can be produced by many different energy configurations. So you assume that they are associated with an average microscopic temperature gradient. So this is the point. The local fluctuation in energy really represents a moment in time when the temperature is not uniform along x1. So the question he posed is, what is the probability that a particular value of alpha 1 at time 0 is followed at a time delta t later by a fluctuation of alpha 2 along x2? And what is the expected average of this quantity? And this can be shown to be proportional to this Onsager coefficient L12 times alpha 1 squared delta t. It is basically the probability that a thermal gradient along 1 leads to a flux along 2. But this is not, remember, because of any externally imposed heat flow. He's saying this is happening in any material which is sitting there at a fixed temperature. There are always fluctuations which are getting attenuated. The reverse probability, that is a fluctuation alpha 2 being followed by alpha 1 from these dynamic reversibility arguments that we argued about earlier, has to be exactly the same. And that, of course, will be minus L12 because of the relationship between L12 and L21. And so, since the mean squared average here of these two is equal, L12 and L21 have to be 0. Now let's look at different types of fluxes. Supposing we have three different effects. Here's an example. Actually, anybody who does electrochemistry will deal with this, whether they like it or not. If you have a heat flux, it can be due to a temperature gradient. It can be due to a potential gradient, that's thermoelectricity, and it can be due to a concentration gradient. So the diagonal terms are the obvious ones where the heat depends on the temperature gradient, the current depends on the potential gradient, the mass flux depends on the chemical potential gradient. Those are the obvious ones. The diagonal terms are the cross terms that we're talking about. And so between heat and current is thermoelectricity, The thermodiffusion is what's called the Soret effect, Soret, I don't know if he's French, heat and mass transport, and electrodiffusion. That's the development of an electric field due to mass transport, or the application of electric field due to giving rise to concentration gradient. So we'll just wind this up with seeing how you can now apply this to thermoelectrics and rederive the Kelvin equations without making those assumptions about irreversibility and irreversibility and so on. So the entropy production rate tells you what the driving forces are. The driving forces here is the electrical potential gradient and this 1 by T. So you write it in these terms so that you understand what driving forces you need to use. Now you make the fluxes proportional to those driving forces. And so this is the flux of electrons, and that's related to the chemical potential gradient or the electrical potential gradient and the temperature. And the coefficients are these Onsager coefficients, L11, L12, and similarly for heat, L12 and L22. And here we assume that these are equal. So we assume that the cross terms are equal because we just proved it. If you do that, the question is, what are these quantities L in terms of what we know as the Seebeck coefficients in terms of thermal conductivity? See, we have not used the same driving forces. There we used the gradient in temperature. Here we're using the gradient in 1 by temperature. So what we call electrical conductivity is nothing more than the flux of charge divided by the electric field when there are no temperature gradients. So there are no temperature gradients, then this term drops out. The electric field is a gradient of the potential when only a voltage is involved. That is, there are no changes in carrier concentration due to temperature gradients. So from this you can derive the electrical conductivity in terms of the Onsager coefficients. And similarly, you can do it for the thermal conductivity. It's a little more complicated. So the thermal conductivity is the heat flux per unit temperature gradient when there is no electron flux, not when there's no potential, but when there's no zero electron flux. Now we can look at the cross terms, the Seebeck coefficient. So here's your junction between A and B at temperature T1 and another temperature T2. You put a voltmeter here. That means there's no current flowing. This is a high impedance thing where you measure voltage. And in the open circuit condition, you can show that the Seebeck coefficient, which is alpha, which is the rate of change, or this is the voltage change due to a temperature difference, is given by these Onsager terms, L12, L11, and so on. And you can do likewise with Peltier. So with Peltier, you have a constant current flowing. So the flux of electrons, which is Jn, in A and B are the same. There's no potential loss between the two. So if you write the internal energy as the sum of the heat and the electrical term, then on one side you have Ju minus Jq, and the other side you have again Ju minus Jq. And this difference in the internal energies of A and B is what is manifest as heat. And today what you would say is that the heat that's evolved is due to the difference in the Fermi levels of the materials across the junction. And so the Peltier coefficient just comes across to be the Seebeck coefficient times temperature, which is the second Kelvin equation. So this is just a summary slide. The familiar way is to write the flux in terms of the potential gradient and the Seebeck coefficient and temperature gradient, and likewise with the heat flux. In the Onsager way, it looks a little different, but now you will see that the diagonal terms are exactly the same, because your driving forces are a little different in terms of the gradient of 1 by temperature. And if you look at the thermal part of it, that is the transfer of heat, this kappa term is of course the traditional thermal dissipation that happens due to conduction. This other term is a mix of, if you just decompose this complicated looking expression, is just a product of the Seebeck voltage and the Peltier current, and that is the part which gets converted to heat. The fluctuations or perturbations in a linear system close to equilibrium, which is what we've been dealing with. So you can use a linear approximation, it's like Fick's law and heat conduction law and so on. If there are fluctuations in a linear system close to equilibrium, it can increase entropy production, but then the fluctuations are damped and the system is forced back to a state of minimum entropy production, as long as the fluctuations are small. But if the fluctuations are large, then something completely different can happen. Then you can get new forms of order, very far from equilibrium, characterized by large energy changes between the system and the equilibrium. And you and I are living examples of large-scale fluctuations which lead to the formation of complex molecules and life and so on. So if you're interested in this, there's a book called by Prigogine. This is that Prigogine, not the one you've been reading about in the newspapers. A book called From Being to Becoming, who took many of these ideas in the 50s and 60s, and the development of non-equilibrium thermodynamics has proceeded very substantially along these lines. But it all started with the notion that there is a concept of entropy production, and that entropy production can be written in terms of a driving force and a flux. So some of you may have got this in your email. So I'll mention it. I mean, it came to me a few days ago, so I'm just putting it here. What the paper claims is that in a real Carnot cycle, you achieve maximum efficiency at a zero rate of conversion. That is, when the process never happens at all, is when you have the thermodynamic limit 1 minus T2 by T1. The faster and faster you try to force the system, the more and more the efficiency deviates from the equilibrium value. That is, the more irreversible the transformation. And therefore, there is a relationship between the time scale over which you're trying to push the system and the efficiency loss. So if I understood the paper right, it says that you can avoid it. This power efficiency trade-off can be avoided. In other words, you can maintain Carnot efficiency even in an irreversible system. Well, it's there. It was published last month or last week. So I'll leave it at this point. I'll just leave you, these are the references. Most of these are available. This collected papers of Kelvin, I should mention, I'm very grateful to the Cambridge University Library for sending it to me. I couldn't find them anywhere else, but you had to read it to see how the ideas evolved. I couldn't find any book which dealt with it because it's too long ago, and the books tend to give you a digested form, not the way in which the ideas evolved. This is the paper by Onsager, Physrev in 1931. Callan's thermodynamics is an excellent source, and this paper by Miller, these papers again are a very readable description of some of these ideas, both from an experimental and a theoretical standpoint. I think that's all I have. Yep, thank you for your attention.
So thank you, Vikram. I'm sure that it was an insightful and thought-provoking lecture. I think the slides will also be available because we'll probably need them to digest the talk more fully. So any questions from the audience? Yeah, Guru.
Onsager's argument, because it uses rate of entropy production, is clear where the second law is being used for the irreversible process. But how did Kelvin pull it off without, or is it implicit in some way that he has done? And
it is, well, it's not the same thing because the Onsager's argument is a statistical mechanical argument. In terms of thermodynamics, it is an arbitrary division into processes which are supposedly reversible and supposedly irreversible. Now, in the case of thermoelectricity, he said Joule heating is irreversible, but the conversion of a current into heat through the Peltier effect is reversible. Now, that seems logical, but there are, like in thermodiffusion, you will find that the diffusion process is treated as reversible in some cases and irreversible in others. It's one way of rationalizing it, but obviously it's not on very firm fundamental foundations.
so we start with microscopic reversibility, and
Correct.
then we look at the entropy production and decide which one is reversible, which one is not
now
reversible.
this doesn't matter. You're not dealing with anything which is reversible or irreversible. You're simply saying, see, if you look into this in detail, you get into this microscopic reversibility runs into this whole problem of if my temperature gradient disappears because of the fluctuation disappears and because things are reversible, then if they're reversible, then they should go back. This gets into those famous controversies about this ergodic hypothesis. I think people are still writing papers about it because even though many very well-known figures in thermodynamics have convinced themselves that there's no paradox, it's not obvious that you're using a process which at the microscopic level is reversible, but eventually there is something called heat conduction which takes it from hot to cold. It doesn't go backwards. So that element is there, but that is there in the whole of irreversible thermodynamics. It is not just...
Professor, it was a very interesting lecture. We went back more than 300 years back and then at present. The question is about this Onsager coefficients. Particularly in ternary diffusion, we diagonalize them. But sometimes we push these Onsager coefficients into zeros and diagonalize them and then use for calculating the inter and then intrinsic diffusion coefficient. what really the Onsager physically means it. Still, I struggle to understand what these coefficients means and when we really keep them to zero, particularly when you are looking in the diffusion, particularly the mass flux. Can you just comment on that?
That's a good question. And I think the strength of the argument is that it avoids discussion of mechanisms. So if you ask, why should a temperature gradient in this direction drive a heat flux in an orthogonal direction? Does anybody have a good, clear, simple answer for that? One could say, why not? Symmetry arguments tell you that certain coefficients ought to be equal in a crystal. If a material is isotropic and this is a second rank tensor, we know that the Onsager arguments tell you it should be equal. If it is a property like the dielectric constant or refractive, it's the same thing.
I argues that these two cannot be experimentally separated out, so you might as well take an average and put them to be equal. That experiment that you talked about, that doesn't rule out. It says that you cannot distinguish even if they are different.
Correct.
You will only
Correct.
get the average.
Correct.
So you might as well put them to be equal, taking the average, assuming that they are.
I was interpreting his question as, why should a, okay, that's a separate issue. Why should a concentration gradient along this direction produce a flux in an orthogonal direction?
And then we put this terms somewhere, diagonalize them and put them, and then we get the most of the diffusion.
So the diagonalization is something that you can do in any system in a second rank tensor. You can always diagonalize it. If it's a symmetric tensor, you can. It's like stress and strain. You can get principal states. So you're simply finding a coordinate frame of reference in which there are no off diagonal terms. That is, a flux in one direction produces. A driving force in one direction produces a flux only in that direction. That part, to me, is not difficult to understand. It is like, instead of having shear stresses and normal stresses, you rotate your frame of reference so that you only have normal stresses. But the question, an intuitive answer to why, if I apply a temperature gradient this way, I should have a flux perpendicular, I don't have a simple answer. You see, for electric fields, I can understand if you distort atomic positions this way, they are going to be distorted in the orthogonal direction. It's the same with stress. You pull something this way and things contract. But for fluxes, it's not. I can't think of a simple answer.
Just a small comment about this thermoelectric effect. Now, thermoelectric effect is no more. Is being useful. Products have been made in the different products, and it is being used and available in large terms. It's no more a kind of fiction or whatever it is.
It's just really that in relation to the amount of research going on, the productivity.
That happens in composites, several things. But then
for elastic, that's a fourth rank tensor. If you take a second rank tensor,
no, but even then it won't work. For the lower symmetry, it won't work. Lower than hexagonal, based on the C by A, it will fall. Orthorhombic, you are gone, and thermoelectric.
But if you take any property given by a second rank tensor, you can always rotate it to a.
No.
You can do it with refractive index.
No,
you can do it with
not for lower symmetry. The refractive index also won't work for lower symmetry. So I'm actually confused.
That 1, 1 and 3, 3 will be different.
It will be.
1, 1 and 3, 3 will be different.
You are talking about the cross 1, 2 versus 2, 1.
If the 1, 2 and 2, 1 is going to be different because it's directional in nature. So if you look at a crystal structure which is asymmetric by nature.
No, what his point was, if you have
I just don't understand.
A set of fluxes and concentration gradients in a given frame of reference, you will have the cross terms as well as the diagonal terms. What he's saying is, if you rotate the frame of reference, you can eliminate the diagonal terms. D11, 22 and 33 are not going to be the same, but you won't have D12 and D21 and D13 and all that. You're just rotating it into a frame of reference where a force in one direction only produces a response in that direction. There is no crosstalk. So there's no, the matrix has only diagonal components. That's all we're saying.
That's not at all true. If you are talking about, this changes the entire argument of something like a twinning shear. It is always directional.
No, that is true. But if you look at a transformation strain, the transformation strain in the coordinate frame of the crystal will have everything. But we are saying that the strain can be rotated, the coordinate system can be rotated to some arbitrary angle, alpha, beta, gamma, whatever, such that the final transformation strain with respect to that coordinate frame of reference is only diagonal. Well, that is true if I have something hot here and something cold here. The temperature gradient is constant. I mean, it's like fixed second law becomes fixed first law if the temperature dependent term disappears. But you have a constant flux. One side is at one concentration, the other side is at another concentration. This is an infinite reservoir here or maintain some activity there. The other side is you maintain some other activity and there's a flux of, I don't know, hydrogen or carbon or whatever. So it's not equilibrium because the two sides are not at the same chemical potential.
All right. Vikram, it was a wonderful lecture and we all enjoyed it thoroughly. So just as a token of appreciation, I have this memento
Thank
for
you.
you from the IIT.